Good day. We're going to deepen our understanding of Cooper Puchta chains in the Condense Matter Physics. Puchta chains, respectively, Cooper Puchta chains. This is a deeper understanding of a long time. This complements the two earlier videos on the understanding of this validated discovery. The world, since Michael Faraday, has dealt with the issue of resistance. The issue of resistance over carbon-induced magnetism. Here is what happens in a Cooper chain, a Cooper pair. The black ferrite, polished, and the round toroids are not magnetized. It's just a representation of what happens when the electrons line up in a straight line in metal because of the smelting, annealing, and drawing process just to make wire. It's just a natural effect, and we spend a lot of time making sure that grain is somewhat straight because we think that's what it needs to flow electricity. That's not true. And we're going to prove that through this very detailed, little bit long video. So please bear with me, because what we did is we decided to take the electrode, machine off some components of it, and look at it in an electron microscope. The results were so overwhelming, we didn't even make it to the electron microscope. There's no need. It's pointless. We're going to show that a little bit later on in this video. So please bear with me, because it will validate what we saw on the oscilloscope on 4-phase power, and this validates superconductivity. It validates condensed matter physics. It answers superconductivity. It answers supercomputing, fixes Einstein, and proves that metals are superconductive at room temperature for this simple reasoning. We will go into this in detail, but I want your undivided attention. Copper is surrounded by round carbon. We know that as a fact. Once the metal cools, it puts a tremendous amount of stress on that carbon. We think that's good. It is not good. We know adding graphene to metal is a good idea. However, it's a fillet of frisbees, and they land wherever you want, okay? We know graphene is flat, but they have the same atomic weight, 12.1. They both have the same Pauling scale, 3.44. However, carbon is 900 meters squared. Graphene is roughly 2,350 meters squared. Well, how can that be? Because it's flat. And if you take something that's round, and then you take something that's flat, and you just add up pi, you're going to get more surface area. Because the electrons of the carbon are in the center. The electrons at the graphene are on the outer valence, and they're set. Supposedly, they're set. Their structure is set, but they have a property. They can be bipolar. They can be a PNP zero gap transistor, okay? Semiconductor, I'm sorry. Which means they can flip polarity very fast. They flip polarity 26 trillion hertz, terahertz. The same frequency that we see in gravity, the same frequency we see in hydrogen deuteride, the same frequency we see in superconductivity. Okay? So here is a little bit of an expansion of the first laying down of the Cooper pairs. And we come through the bow tie of superconductivity. I call it a bow tie because I'm the person bringing you the understanding of superconductivity, and you're still trying to figure out what superconductivity is. And I've been working with it for a validated 10 years. I built the first linear magneto circuit in 2005, 2006, and it worked the first day. I've spent in this entire time building products, selling the components that work on these principles. Now we're bringing this to the world because we need it right now. We need to save our oceans. Our oceans are our oxygen. That is the cause of the CO2 global warming issue. It's the electromagnetism over our grid. Please pay attention to my CO2 capture page, but I'll just repeat it again because it's worth the moment. Yes, CO2 is a reflective heat. Fine. That's not the problem. It's a symptom of the problem. The CO2 in the atmosphere stops the linear energy at 201 microamps in the atmosphere. The videos on top of Linear Paul Magnetism prove that without a shadow of a doubt. The first two videos are Linear Paul Magnetism, Superconductivity, running on its own power. The video below that is a Bose-Einstein condensate above room temperature where the electrons go into a wave exactly at 201 milliamps. It snaps into a Bose-Einstein condensate. The electromagnetism is encapsulated by the linear magnetism, and photosynthesis does not happen. Cyanobacteria is grown with photosynthesis. It cannot be grown with electromagnetism or the sun. It is the cyanobacteria that gives us our oxygen. It gives us our fuel. It gives us our food for our fish. Our fish defecate. Our fish defecate, the corals eat the defecation and they grow. They have to have that food or they cannot build a calcium carbonate shell. Exoskeleton. All creatures with exoskeleton, okay? That's why the shrimp, krill, and lobster turn red. That's why salmon turns red when it changes to an oxide swimming upriver from the axanthin from the cyanobacteria. It's the same thing that fills up our oil wells. Fine. We burn the oil. It fills up the ionosphere. The ionosphere gets carbon conductive. Once the ionosphere gets carbon conductive, the linear energy stops. The pollution from United States of America and the electrical grid at nighttime energizes the ionosphere. The earth turns too fast and the photosynthesis cannot happen in the coral reefs. Can you please hear me? Greta Thunberg, I'm answering you. Now, let's move forward. Come through the bow tie of superconductivity. Now, the electrons are imposed on the graphene. How do we know that? Because for the first time in 10 years, I got to catch it on an oscilloscope so that I can prove it to you without a shadow of a doubt. I would not come to this table unless I knew that I could prove it, okay? So I waited and I waited and I waited, and finally I was able to catch it on an oscilloscope. And then we documented it. We're smart enough to turn on the camera and document it. So what happens is the electrons get imposed onto the graphene. I assumed, okay? As I studied it more and more, I realized that it's even better than that. What happens is the graphene allows the electrons to tunnel through the graphene. Not just go around like they have to on carbon. We'll show that in a second. But I'm giving you a brief understanding so that we can go in a little bit more detail. You can see on the oscilloscope that the four-phase power, linear energy, linear magnetism, allows room. It's spread open the wire. How do we know that? We can see it on the oscilloscope for the first time. The Cooper pairs have been a theory because nobody's been able to see them on an oscilloscope. It's just been an accepted theory of what's going on. So now the electrons, they come and they kiss and they say thank you, and then they move out into a heterodyne and go again. That's a great understanding, and it seemed to be satisfied enough until I looked in the microscope, and it told me the true story of what's going on and everything that we know about graphene. Okay? So let's move forward. Now, these ring magnets underneath of here are the only things holding these structures together. I let magnetism control this demonstration. Okay? There's just a little super glue between this toroid and the magnet so that I can move them around and they won't move. Okay? So during the Cooper pair, the graphene is round and we've got two electrons in the center of the graphene. There's no place for compression because the carbon is at its ground state. And so what we're going to show you is that graphene is the number one. Carbon is the allotrope of graphene. It needs to move up. It's not an isomer of graphite. That's just where we found it. But it's actually number one because the way it comes from the sun, it comes from fusion. And when you impose an electron during the combustion process or the steel process, you compress that graphene that's in nature down into carbon. We have to think that way. Okay, so thankfully that Art Divine, Dr. Divine, who owns Magnetic Arts, who gave us the gigabyte, it was Arthur Divine, Dr. Divine, my chief technical officer when it comes to condensed matter in the magnetic moment, because he brought us the recording head that went from 1 megabyte to a gigabyte. Without him, we would not be where we're at. Okay? Very important. All these toroids, they're matched. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and all the way around. Everything lines up copacetically. Here's the problem. The carbon, like I said, there's no room. This is indicating the inner valence and the outer valence and the magnetic field. So we carry that through this entire demonstration so that we're square, because we got to go back to magnetism, but we have to add one more element to the magnetism. We have to add linear magnetism, because that's our pathway to understanding the amplification that I've been showing you of gravity, because gravity is superconductive. The sun is superconductive. We get the heat from there, but the fusion reaction is technically cold. Okay? We prove that in the videos. I understand the hydride proprietary formula for the fuel for fusion. Thankfully, it's affordable. It's not open source, but it's affordable because it needs to be licensed in the proper hands. And it's not going to the greed of the oil companies. I can guarantee you that. It's in my will. So, here's what happens. Here's a Cooper pair. Here's a carbon atoms, okay? All lined up nice and neat through the annealing and drawing process of wire. So this one, you can see, there's the compression. There's the spread. There's the rebound. Lined up magnetically, naturally. That's what happens in metal as the electrons try to get through the carbon around the balls. Okay? Pretty simple when you look at it this way. So let's move these now that you understand, and we can just squeeze them. See that? Pretty simple. And that's all just magnetism, moving everything where it needs to be. Then we move to the next one. It's a little bit more rough because I've got it tight. Move to this one. Sorry, I glued this one to the bench. We're going to have to move on to something else. There we go. Okay. And so it gives us the opportunity, excuse me, it gives us the opportunity to move the carbon atoms around in the lattice. And the electrons still follow the path. See that? I glued that one, I'm sorry. We'll move these ones around. And everything can move around and find its order. And the electrons can go around. This is something that we understand. This is a nice visual demonstration of that. Now we have to move over to what's really going on when we convert the carbon in the wire to graphene. Give me 1 second. The superconductivity of the magnets is unstable. And I'll show you that in a minute. And it keeps jumping to this demonstration that I'm going to show you. So I'm trying to fix it while I'm talking. Okay? It's being a little tenacious. That's fine. I like to have a little organic videos. I don't like to edit them because I don't want you to think that we're doing sleight of hand. Okay. Now, this is a representation. I just let it go together by itself. There's only crazy glue here, 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 and here. The rest is held together by magnetism. And as you can see, it can be moved in any direction. So I let it flop, and it happens to flop in the same configuration as the four-phase power that you see on the oscilloscope and the Cooper Puchta chains, representing the electrons. Now, these electrons on the outside, they can be either the graphene electrons, or they can be the imposed electrons. It doesn't matter. We kind of know that when it comes to graphene. However, now that the graphene is flat, it's in a protected pocket of the metal. And so that flat graphene can gyrate like a gyro in any given direction it wants to go in the metal lattice. It's infinite. And when it's spinning, it picks up the coming magnetic field, not the induced magnetic field. So this also proves that voltage brings the magnetism, like in linear Paul magnetism, where the voltage comes first, the amperage comes second, okay? Contrary to Michael Faraday. And it doesn't matter which way you look at it, and any way you hook it up that you've seen during the demonstrations. Now the generator, as you've seen, is putting out more amps, more volts, same ohms, not ohms, same hertz, but 50% perfect power. Perfect power anywhere up and down the power grid, because the graphene it knows that signal's coming. The carbon has to be induced. There's the amperage, okay? Here, the graphene can go any which way it wants, and it can shoot at any angle. It doesn't matter, okay? It can tunnel. Now we've understand tunneling, quantum tunneling. This superconductivity answers quantum tunneling, because the graphene, if the electrons are solid set around the outside of the metal lattice, okay, the graphene, it's rotating and spinning, so it lets the electrons through its tunnel, just like a revolving door. But it knows it's coming because the voltage comes first. The voltage does the work. Amperage does not need to do work in superconductivity. It's a brute, and I'm telling you, you've seen a brute of amperage come out of superconductivity. So now that you've seen this, we can mess with it. It doesn't matter which way it turns. It will still hold the electrons. This demonstration's good enough for you to understand why we see the four waves on the internet, on the oscilloscope. The electrons can tunnel through, and it can move in any direction on demand, anytime it wants. Okay, now let's move forward to the tunneling effect. We'll stay with tunneling, and we'll try to stay using physics terms, because everything except for the name Linear Paul Magnetism, which I define in physics, is a trade name, a trade phrase. The word magnetism is trademarked to me because it's spelt based on magna, earth, and the Z denotes the Z-axis in gravity, magnetism, phonetically spelled. Okay, Now we understand the electron, boop, it can go right through the middle. No problem. Or it can go around the outside, as you see. Okay? No problem. Has no problem. Because it doesn't have to move anything. Okay? No problem. So we're going to put it in the middle, just for demonstration. See that? No problem. It finds its point, and the electron, excuse me, it's a little jumpy, but it's not magnetism. It's superconductivity. It's linear magnetism. Watch. They're just different polarities. That's it. So we're going to represent how the graphene lattice, the chain, can sense the coming voltage and correspond and respond before the amperage or the voltage even gets there. So technically, the magnetism comes first in superconductivity, and the voltage is second. But your potential, when you drive the linear circuit, the voltage comes first. But as it comes through the bow tie and you're imposing superconductivity over magnetism, the magnetism comes first. Here's the visual representation of that. Pick up this one, but you see, I'm going to be I don't have to be very light. This is not two magnets opposing each other, okay? This is linear magnetism. It's not a ball. It's a field. It's a field, and it's not a primer field. This is a lot of respect to David LaPont, but this is not a primer field, okay? David LaPont's primer field is based on electromagnetism, which is the sun's light energy. This is the sun's brute force energy that pushes the heat and light, okay? This is a field. This is just a field. But see, there's no attraction. There's no attraction yet. They're all lined up the same. Now watch. Oh, I'll pick up this one, I'm sorry. Now watch. Now the field is moved down here. But all I did was flip this one. The rest are stacked the same. Okay? You see that? I'll take this one and I'll flip it. Once I flip it, it becomes just like this one. This one will pick up the whole stack, but you can see they're not glued together. So as the energy goes through, it says, okay, thank you, revolving door. Boom, get out of the building. And bumps it forward faster. That's how the electron can go faster than the speed of light. However, the University of Los Angeles in the 50s proved that hydrogen, a heavy hydrogen solution, the proton hops faster than the electron. Put that feather in your hat for a moment. We'll talk about it later. We'll stay on electrons. This one, this one, the field is square. But it's not the same field as this one. In graphene, you have 3. We know that. But now we have 6. We have 1 pushing, 1 pulling, 1 solid, 1 pushing, 1 pulling, and then the other potential solid. So this is the ground, and these are the two switch legs in superconductivity. So these two are your heteros, and this is your heterodyne. This is your third frequency. This is your ground state in heterodyne. In heterodyne magneto, which is linear Paul magnetism. That's why the ground state of the energy, I can overcome Michael Faraday, no problem. Pretty interesting, huh? I think so. And I think it's worth noting. And I think the world needs to know this, so that we can move forward as fast as we possibly can. Because we are in a situation. Here's where we were. Here's where we're going. And unfortunately, this is where we've been. This is how we got here. The sun got us here. Hydrogen produces graphene. Now, let's move on to the refractive light microscope. So we cut the stainless steel off of the tip of the electrode. Saved the shavings, because as I was cutting through the stainless steel electrode, it cut like butter. And I was expecting the skin effect in my electrodes. Never really paid much attention. I just knew that there's got to be a property of superconductivity, because you cannot hold a red hot electrode on one end and the other end be cold. So we decided to take a chance and take a look. Okay? Let's see if we can square this so you can see it. Give it a second. Okay. I think we'll be okay right there. Yes. I'm just setting everything up so you can see. So what you're going to be looking at is the color. There we go. Please bear with me. This is important. Okay. This is the regular stainless steel. You see the color? And you see the grain. Bear with me. Okay, you see the grain. Nice and straight. I apologize for the light reflecting, but this is the best I can do because the TV doesn't work at the moment. Okay. Not too bad. We're looking at some carbon on the cold side of the metal shaving cut. Now we're going to go to the hot side. This is where the bit machined. Let me see if I can do something here. Okay, we're just going to have to deal with this light flicker. It's the best we can do. Okay. Now, this is a refractive light microscope, so if I go up, that tells me that the material is less dense. If I go down to focus, that tells me the material is more dense. So we're going to set the density on regular 304 stainless steel and try to get a focus. We're going to go to a higher power after this that's much more crisp, but just please bear with me. Okay. There. You see the gold color? That's the chromium in the stainless steel. Now let's go to the electrode, same side, the hot side. Now look at the metal. You see the color difference? It's pure. There's no more chromium. And I have to go down with the microscope to get you focus. That means the metal is more dense. Okay, that looks good. And it's much more reflective. Now we get a nice, we don't get the spot that we got from the camera. We get a nice, even light distribution. That would also indicate superconductivity, because superconductivity controls light as well. It's something that we don't see in the door of superconductivity, but it's something that I have observed. So I just want to bring that to your attention because it relates directly to Maxwell Planck and the phonon resonance. Okay, now we're going to move forward to the dark side. Now I have to go more dense. Look at the condensed matter structure now. And I'm getting a good light reflection from the camera. But look at the grain structure. Give me a second. It's wavy. It's interwoven like carbon fiber. It's not straight anymore. proving we changed, excuse me, I'll talk while I'm rearranging this. We changed the condensed matter, the atomic structure of the stainless steel, which would imply that we changed the metal in the generator, because now the generator is producing voltage just standing there. That's the definition of superconductivity, the energy, the electrons running free. Now it induces the linear magnetic wave, taking Tesla polyphase and completing it with my copyrighted circuit. I think you understand what that means. Okay? So now what we have to do is we have to have a little bit more patience. And we're going to look at it at a higher power. You see the grain structure now? You see how it's woven? And it's very dense. I have to go up and down quite a bit to give you a good view at any one of the hips or valleys. See that? Okay, now let's look at the electrode on the hot side of the bit. You see how it peeled? It didn't smear when the cobalt bit, because it wasn't tool hardening, it was cutting nicely. There's no smearing between the cracks. Okay. Okay, so we're going to set our focus right about there. And we're going to hold it steady and go over to the hot side of the regular stainless steel. Let's find a nice sweet spot. You already see the color difference before I even focus. Now I have to turn the wheel up. It's less dense. You see how it's smeared? It didn't cut, and that's one of the problems with stainless steel for tool hardening. Okay. Now let's go over to the dark side of the metal. Now I have to take the microscope. I got to go back in because it's a little bit more dense. You see how the grain is nice and straight from the annealing and drawing process? Proving we changed the condensed matter. In regular old stainless steel. A little bit harder to change than copper. You saw the video of 303, and if you're paying attention, I'm going to load the last part of the video. I'm going to spoil it though. If you're paying attention this far, you'll notice that the gold was at the end of the tort in the 303 video, but once it completed and the AU-197 came down out of his radioactive state, well, you're just going to have to watch the video to see what happened. Back on subject. Nice straight grain, to be expected. To be expected in a drawn stainless steel. Probably came out of a big billet, took a couple miles to get us nice, or a couple hundred feet at least.